Welcome to my next video, APES students. This is chapter 19, Global Change. So, starting off with module 62, what are we going to be talking about? Global climate change and the greenhouse effect. So, in this module, you should be able to distinguish among global change, global climate change, and global warming, explain the process underlying the greenhouse effect, and identify the natural and anthropogenic sources of greenhouse gases. Let's get into that first point. We've got global change, global climate change, and global warming. Three terms that are most likely going to be helpful for something more along the lines of an FRQ. Knowing the different levels of depth are going to help you figure out what you should be writing. So for global change, that is a change that occurs in the chemical, biological, and physical properties of the entire planet. So then, global climate change is going to be a change in the average weather that occurs in an area over a period of years or decades, right? So we're talking about the change of weather, the day-to-day temperature, precipitation. The average weather of an area is going to change. So when we have a global climate change, that means there are large patterns of these climates changing. Then for global warming, that is simply the warming of the oceans, land masses, and atmosphere of the Earth. And there is, especially in the news, some confusion between those last two terms, global climate change and global warming, where they are often confused between, well, it's cold outside, there's no global warming, when really the person's trying to talk about global climate change. So understanding the difference between these two terms will be very important. Here are some examples for each of the different terms so that we get a better idea of what they're talking about. So for global change, you've got rising sea levels, increased extraction of fossil fuels, increased contamination, altered biogeochemical cycles, and again, these are just changes that are happening on a global scale. For global climate change, you have increased storm intensity, altered patterns of precipitation and temperature, altered patterns of ocean circulation, and global warming. All of these have to do with the changing climate on a global scale. And then lastly, with global warming, you see that there is the warming of the planet's land, air, and water, increased heat waves, and reduced cold spells. So again, if there's an FRQ asking about something specific to global climate change, something from that box would definitely be helpful rather than something from the global change, which is not exactly talking. When we talk about all this warming, well, where is it coming from? So solar radiation and greenhouse gases make our planet warm. When radiation from the sun hits the atmosphere, 1/3 is reflected back right out into space. Some of the UV radiation is absorbed by the ozone layer, and the remaining UV passes through the atmosphere and strikes the Earth, where it is then converted into a low-energy infrared radiation. So it's coming in as UV, as visible, it's getting absorbed by the Earth, and then re-emitted or converted into this infrared radiation. The infrared radiation then goes back toward the atmosphere where it is absorbed by greenhouse gases that radiate most of it back to Earth. So it's as if it is being caught by these greenhouse gases as it's trying to escape Earth, and it's being sent right back down. That's what's trapping this heat and making it warmer. So the greenhouse effect then is the absorption of infrared radiation by atmospheric gases and the re-radiation of the energy back towards Earth. So again, it's being caught by these gases who like to absorb the infrared radiation. They re-emit it in a random pattern, and a whole bunch of it gets sent right back down to Earth, making it stuck in our atmosphere and making it warmer. So in this image, if you follow the numbers, we can see all of this process happening. So the incoming solar radiation, point 1, consists primarily of UV and visible light. You can see that those yellow arrows are going right through our atmosphere and touch down on the surface. But before it does that, point 2, about 1/3 of the solar radiation is reflected from the atmosphere, clouds, and the surface of the planet right back into space. And you can see that if you follow my mouse right over here, right? You see some of it being reflected here by the surface and by the atmosphere and clouds. So it is not fully getting to Earth and heating it. Then step 3. The remaining solar radiation is absorbed by clouds and the surface of the planet. Both become warmer and then emit infrared radiation. So absorbed by the surface, absorbed by the clouds, and then you get to 4. Much of the emitted infrared radiation from Earth is absorbed by greenhouse gases in the atmosphere. The remainder is emitted into space. So you can see the greenhouse gases, and they're showing it as a layer here, and that is slightly true, right? CO2 is going to be more concentrated in the troposphere than in other areas, but let's just look at this as part of a diagram rather than it being an exact single layer. So much of the infrared is going to interact with these greenhouse gases, be absorbed by them, and then re-emitted back down, while some of it will escape. This is not all bad though. The greenhouse gases here, taking in all that infrared and emitting it, some of it back down to the planet, have kept the planet at a reasonable temperature for life to evolve. Without it, we would be very, very cold, and most likely things would be very different. So thinking of the greenhouse gases as a negative is not necessarily a good thing to do. As the greenhouse gases absorb infrared radiation, they warm and emit infrared radiation back, with much of it going back towards Earth. The greater the concentration of greenhouse gases, the more infrared radiation is absorbed and emitted back towards Earth. It's when these gases are too concentrated and they are doing their job too well that we start to get into this global warming and global climate change situation. So other than CO2, what are the gases that cause the greenhouse effect? The major greenhouse gases are water vapor, H2O, carbon dioxide, which I think we all know at this point, CO2, methane, CH4, nitrous oxide, N2O, and tropospheric ozone, O3. But not all greenhouse gases are created equal. The contribution of each gas to global warming depends in part on its greenhouse warming potential. So what is that? Well, it's an estimate of how much a molecule of any compound can contribute to global warming over a period of 100 years relative to a molecule of CO2. So in this chart, carbon dioxide is our baseline to be used for comparison. And there's two things we have to worry about for the other gases to see how they stack up against it in terms of their effects. So you have to look at their ability to actually absorb the infrared radiation and then re-emit it, but also you have to look at the duration that these gases are hanging around in the atmosphere. So if you look at water vapor you can see in the, if you follow my mouse again, you can see it is lower than 1. It is not as potentially warming as carbon dioxide in the long term. Right? It does not stay in our atmosphere for very long, although there's a lot of evaporation bringing it right back up, and it is not going to be absorbing as much per molecule compared to carbon dioxide. But if you take a look at methane, nitrous oxide, and chlorofluorocarbons, they are going to have a higher global warming potential. So methane with 25 times the amount as carbon dioxide, nitrous oxide 300 times more effective at globally warming, and then chlorofluorocarbons with an astronomical 1,600 to 13,000 times greater potential for warming our planet. And this all has to do with, again, the ability to absorb that infrared and the duration that they stick around in the atmosphere. Methane sticks around for about 12 years, nitrous oxide 114 years, and then chlorofluorocarbons 55 to 500 years, or just below. So they definitely are hanging around, and they are going to be able to absorb that infrared, and that's why they're so much more impactful. Where does all this stuff come from? All these gases, where are they coming from? Sources of greenhouse gases are both natural and anthropogenic. So, some greenhouse gases are produced from natural sources such as volcanic eruptions, which we've talked about in the past, especially with sulfur dioxide. That's not a greenhouse gas, but just another thing that volcanic eruptions can lead to. So what are they actually bringing to the greenhouse front? They're bringing ash and they're bringing carbon dioxide. Decomposition and digestion are going to bring methane. Denitrification is going to bring nitrous oxide, and then evaporation and evapotranspiration will bring water vapor. So on the human cost side, what are we bringing to the table? Some greenhouse gases are produced by human activities such as burning of fossil fuels, agricultural practices, deforestation, landfills, and industrial production. Take a look at this picture, you can see, right, you've got some cars giving off some CO2, some NOx, you've got industry, right, more CO2 from fossil fuel use, factories, all giving off, again, that ash and that CO2. The landfill, if there's any organics in there, will give off the methane. Same thing with these cows who are going to be producing methane as they eat and digest all that grass. Deforestation is going to let go of a bunch of CO2 that was sequestered in its trees and its soil. And then also you've got this tractor, which is going to be also using fossil fuel, giving off CO2 and potentially also leading to NO2 if it is putting down any fertilizer. Three major anthropogenic greenhouse gases that we'll talk about: methane, nitrous oxide, and carbon dioxide. We want to know, where are we making the most of these things? So if you look at these different pie charts, you can see with methane that energy production and combustion is going to be the largest chunk with 41%, followed by livestock digestion at 23%, and landfills 17%. For nitrous oxide, a whopping 69% will be from agricultural soils, from all that fertilizer. And then lastly, for carbon dioxide, you've got 38% combustion to generate electricity, you've got 31% combustion for transportation, and you've got a smaller 14% for industrial processes. So now that we have an understanding of the greenhouse effect and global climate change, what is the evidence for global warming? That leads us to Module 63. So after reading this module, you should be able to explain how CO2 concentrations have changed over the past 6 decades and how emissions compare among the nations of the world. Explain how temperatures have increased since records began in 1880. Discuss how we estimate temperatures and levels of greenhouse gases over the past 500,000 years and into the future. And lastly, explain the role of feedbacks on the impacts of climate change. So one part of our evidence is that CO2 concentrations have been increasing for the past 6 decades. If you look at this graph from 1954 to 2014, you can see that there is an overall trend with that blue line, with also that weird zigzag pattern that happens seasonally as our northern hemisphere tilts towards the sun and has a whole bunch of spring. Then in our winter, or the southern hemisphere summer, there is a decrease in the total amount of plant life. So CO2 is actually being emitted back into the atmosphere as things die off, and you get this zigzag or up and down pattern from the seasonal variation in CO2 taken by. This increase over time is correlated with human emissions increase. We've seen that CO2 is a greenhouse gas, which is going to contribute to the greenhouse effect, but also there is something else we need to worry about, which is ocean acidification. This is the process by which an increase in ocean CO2 causes more CO2 to be converted to carbonic acid, which lowers the pH of the water. This is not so good for things that rely on specific pH ranges and can lead to a whole bunch of critters not being able to actually have their shells, which are made of something that is basic, calcium carbonate, and so this can lead to some really bad circumstances for things that are in areas where it is too acidic to actually even make their shell. We also have to worry about coral. Provides a large habitat for a lot of marine species, and so if they are not being able to survive or propagate due to increased acidity of the water, then we're going to have huge problems in those underwater ecosystems. So who's giving off the most emissions of CO2? Well, if you take a look at A, China and the United States are definitely the huge leaders in terms of making the most CO2 due to emissions. So this is in millions of metric tons of CO2, and China is certainly in the lead as a nation. The strange thing is, if you look at B, you can see that some of the major CO2 emitters have relatively low per capita CO2 emissions. China, which is the number one on A, right, it is making the most as a nation, actually has a lot less per person or per capita than the United States. But this makes sense. Places that are developed and have a large amount of industry are going to be making more CO2. So if you are in a developed or a developing nation, you are going to be definitely on the higher end of this list. And that's exactly what we see in B, in the per capita metric tons, where all of those different places, the top 10 or so, are all definitely developed nations that are contributing to CO2 emissions. So with the increased CO2 levels, what's been going on with temperature? Well, global temperatures have steadily increased since records began in 1880. If you take a look, you can see that from 1880 to 2010, the temperature has gone up 0.8 degrees Celsius, or 1.4 degrees Fahrenheit. You might be saying, 0.8 degrees Celsius, that doesn't sound like it would do very much. But you have to consider that this is an average of the entire Earth. So some places that remain the same temperature are going to make other places, since this is an average, or it's going to mean that those places are increasing much, much more in temperature. So some places will have very, very high temperature compared to all the places that don't have a temperature increase. So yes, while it may seem like 0.8 degrees Celsius isn't very much, that doesn't actually account for each individual place and how they are being affected. Here is a map that more clearly illustrates the differences in temperature changes over that period of time. If you are in the dark red or orange, you can see that that is higher up in that change. So if you look up at the North Pole has certainly undergone the highest temperature changes. You can also see at the South Pole, though, there have been some negative changes. So you can see that there's those small splotches of light blue and more aqua blue. So those have actually gotten cooler a little bit. But overall, the change is that there is a warming across most of the Earth, and it is hitting those polar ice-bearing regions harder than the rest of the Earth. So from 1880 is not a very large amount of time. What if we want to know further back than that? Well, scientists can estimate global temperatures and greenhouse gas concentrations for over 5,000 years. Well, how do they do that? Well, we use ice cores from glaciers, and we look at air pockets that are stuck within them, and we can actually get a good indicator of the gases that were present, and we can figure out temperatures from those concentrations. Specifically, we can look at oxygen 16 and oxygen 18. Ice formed during a period of warmer temperatures will contain more of the oxygen 18 rather than the 16, and they call that heavy oxygen. So we can look at the gas in these air bubbles stuck in this ice, right? As ice is building up from snow that gets compacted, it traps these air pockets. And so if you look at the oxygen 18 and 16, if there's more 18, we know that it was a warmer temperature from that. From those greenhouse gas concentrations that we find, along with the temperature assumptions that we can get from oxygen 18 and oxygen 16, if you plot these both out together, you can see that they are highly correlated. So in other words, they are two factors that are varying together over time, and since they are matched so well, we can assume that they are tied together. So the question is, where is the temperature going? Look, these are some predictions for what would happen if we had a low increase in CO2, a moderate, and then a high increase in CO2. And as you can assume, the more CO2 that is increasing in our atmosphere, the higher the surface temperature change will be, because that infrared is being blocked from escaping, and so it's going to be making the surface warmer. When we're talking about this increased temperature for the Earth, we also want to talk about feedback systems. Now, feedback systems we've talked about in previous chapters, a positive feedback system being almost a runaway effect, and a negative feedback system being something that likes to come back to a stable level. Higher levels of CO2 promote higher temperatures. When temperature increases, you get higher temperatures, leading to faster decomposition. With decomposition, you get faster decomposition, boosts the rate at which CO2 is added to the atmosphere. Right? Things are breaking down, so they are going to be emitting more of that stuff quicker, and so that's going to again bring you back to higher levels of CO2, promoting higher temperatures leading to even faster decomposition, and so on and so forth. So it's a runaway effect. For the negative, you have increased atmospheric CO2 increases plant growth. Then, because you have that increased plant growth, that's going to increase the uptake of CO2 from the atmosphere, thereby decreasing the amount of CO2 in the atmosphere. So when you have this back and forth, this is going to remain quite stable. These feedback systems both do have their limits, though. There's only so much that decomposition can be decomposing, so there's a limit to how much CO2 could be being brought into the atmosphere at a certain time. This is also true for plants. Sometimes the limiting factor is not CO2 that will encourage the growth, but something else, another nutrient such as nitrogen or phosphorus, or it could even be. So large amounts of CO2 will not always lead to increased plant growth. This leads us to Module 64, Consequences of Global Climate Change. So after reading this module in your textbook, you should be able to discuss how global climate change has affected the environment, explain how global climate change has affected organisms, identify the future changes predicted to occur with global climate change, and explain the global climate change goals of the Kyoto Protocol. Here is a list of all of the things that are happening already to the environment due to global climate change. So you've got the melting of the polar ice caps in Greenland and Antarctica, the melting of many glaciers around the world, the melting of permafrost in the the rising of sea levels due to the melting of glaciers and ice sheets, as well as the fact that when water warms, it expands, so that on a ocean depth, right, if every part of water is slightly expanding, if you extrapolate that out for the entire ocean, that can be really, really big in terms of its overall effect. Heat waves, cold spells, change in precipitation patterns, increase in storm intensity, and a shift in ocean currents. So as we mentioned in the last module, a lot of the northern hemisphere has been hit by the highest changes in overall temperature. So what effect is that having on the ice cap? Well, the ice cap is having more melting. So if you look at this graph, you can see the millions of kilometers, the extent of those ice caps have been declining, and this is taken from each part in late summer for each year, because that is when it is at its minimum, and you can see that it is hitting lower and lower minimums each year because it does fluctuate as it gets colder and warmer with the seasons. So you can see though that the trend is downward. On the positive side of the ice cap melting, this will open some ship trade routes and potentially give us access to some resources that were buried under ice. On the negative side, the ice cap is very reflective, and that is actually reflecting a good amount of sunlight during the summer. So if you are going to be getting rid of that ice, which is more reflective than ground or water itself, you are going to be also contributing to a slight positive feedback cycle where more ice melts, then it's going to get warmer, warmer temperatures lead to more ice melting, and so on and so forth. This is also the trend we see with two glaciers that are depicted here, the Antarctica and the Greenland graphs that we see. Both of those are losing the thickness of their ice, and that is listed in ice mass in gigatons. They're losing thickness, and that loss of thickness is water that is entering the ocean, leading to that increase in sea level. So what about organisms? So global climate change is already affecting organisms. Wild plants and animals can be affected. The growing season for plants has changed, and animals have the potential to be harmed if they can't move to more appropriate climates. We talked about this in the last chapter, where if you cannot adapt to the change in the environment, or if you are not mobile enough to get out of there, then you are going to have a hard time and potentially become threatened or even extinct if you can't live there. Humans may have to relocate. Some diseases like those carried by mosquitoes could increase, and there could be economic consequences. Corals are also particularly sensitive to global warming because the band, should say, of temperature tolerance is quite small. We mentioned this in the previous module. Coral is very important for coastal reefs. So if you are getting rid of corals, you are taking away habitat for fish that depend on them. So with all these issues, what's being done? The Kyoto Protocol addresses climate change at the international level. So everyone in the world was worried about the effects of greenhouse gases with the temperature increases. I mean, this is a problem on a global scale. So in Japan, there was the Kyoto Protocol, which was an international agreement that set goals for global emissions of greenhouse gases from all industrialized countries to be reduced by 5.2% below their 1990 levels by 2012. Although the United States signed the original Kyoto Protocol, the U.S. Congress never ratified the agreement, and the protocol has never legally been binding on the U.S. The U.S. was unhappy that developing nations weren't hit by as hard of a reduction and said that that was unfair economically to the U.S., where now they would have to change a lot of their industry to be more clean, whereas the developing countries could still be emitting, which would cost them far less. But the U.S. in 2005 had 141 U.S. cities, and both major political parties gather in San Francisco to organize their own efforts to reduce the causes and consequences of global warming. Overall, the Kyoto Protocol has been successful, reducing many of the developed nations' emissions by large percentages. For example, Germany reduced their emissions by 25%, and Russia reduced their emissions by 34%. The US has also done pretty well in terms of reducing their overall emissions. In 2012, the Obama administration put into effect an increase in fuel efficiency for most vehicles across the board. So this, in conjunction with some other efforts by the Clean Air, have definitely helped the emissions become lower, just like the other nations, even though we never actually fully signed on to the Kyoto Protocol. Lastly, we'll talk about carbon sequestration again. So carbon sequestration is an approach to stabilizing greenhouse gases by removing CO2 from the atmosphere and leaving it somewhere else, essentially. So some methods include storing carbon in agricultural soils or retiring agricultural land and allowing it to become pasture or forest. As you are having more plant life grow, it's going to be taking up that carbon dioxide, which will keep it out of the atmosphere. Researchers are looking at cost-effective ways of capturing CO2 from the air, from coal-burning power stations, and from other emission sources, cutting it off from the source, which would be very good. And then lastly, captured CO2 would be compressed and pumped into abandoned oil wells or even into the deep ocean where it would be stored. So that is the wrap up for Chapter 19. See you soon.